Hello class, this video lecture is on sensor technologies. It's for the course ME391, Binghamton University, in the spring of 2021. So in this lecture we will look in detail at the range of sensors available for measuring various physical quantities. And you can see quite a range of sensors here. As we study these sensors, we will quickly come to realize that a wide range of different physical principles are involved in their operation. It will also become apparent that the physical principles on which they operate is often an important factor in choosing a sensor for a given application. That's because a sensor using a particular principle might perform much better than one using a different principle in given operating conditions. It is therefore prudent to devote this lecture to a study of the various physical principles that are exploited in measurement sensors before going on to further lectures devoted to measurement of various physical quantities. The physical principles that we shall examine are capacitance change, resistance change, magnetic phenomenon, including inductance, reluctance, and eddy currents, the Hall effect properties of piezoelectric materials, resistive change in stretched strained wires or strain gauges, properties of piezoresistive materials, and ultrasonic properties of ultrasound. It must be pointed out that this list of technologies is not a full list of the technologies that are used in sensors, but rather a list of technologies that are common to several different sensors that measure different physical quantities. Many other technologies are used in the measurement of single physical quantities. Temperature measurement is a good example of this, as several of the sensors used are based on technologies such as resistance change and voltage change. Capacitive sensors consist of two parallel metal plates in which the dielectric between the plates is either air or some other medium. The capacitance C is given by this equation. Absolute permittivity is defined as the measure of permittivity in a vacuum, and it is how much resistance is encountered when forming an electric field in a vacuum. Relative permittivity is defined as the permittivity of a given material, in this case the dielectric separating the plates, relative to that of the permittivity of vacuum. Permittivity is a measure of the electric polarizability of a dielectric. Polarizability refers to the tendency of matter, when subjected to an electric field, to acquire an electric dipole moment in proportion to that applied field. There are two types of capacitive devices which differ according to whether the distance between the plates, that distance d, is fixed or not. Capacitive devices in which the distance between the plates is of variable size are primarily used as displacement sensors, and that makes sense. You know, the capacitance is going to change as d changes, so you can measure the distance between the two plates by measuring the capacitance. Such devices can be used directly as a displacement sensor by applying the motion to be measured to the movable capacitor plate. Capacitive displacement sensors commonly form part of instruments measuring pressure, sound, and acceleration. In the alternative form of the capacitor, the distance between the plates is fixed. Variation in capacitance is achieved by changing the dielectric constant of the material between the plates in some way. One application is where the dielectric medium is air and the device is used as a humidity sensor by measuring the moisture content of the air. Another common application is as a liquid level sensor, where the dielectric is part air and part liquid, according to the level of the liquid that the device is inserted into. Resistance sensors rely on the variation of the resistance of a material when the measured variable is applied to it. This principle is commonly applied in temperature measurements using resistance thermometers or thermistors. It is also used in displacement measurement using strain gauges or piezoresistive sensors. In addition, some moisture meters work on the resistance variation principle. Strain gauges are devices that experience a change in resistance when they are stretched or strained. They are able to detect very small displacements, usually in the range of 0 to 50 micrometers. And they're typically used as part of other transducers, for example, diaphragm pressure sensors that convert pressure changes into small displacements of the diaphragm. Measurement inaccuracies as low as 0.15% of full-scale reading are achievable, and the quoted life expectancy is usually 3 million reversals. Strain gauges are manufactured to various nominal values of resistance, of which 120, 350, and 1000 ohms are very common. The typical maximum change of resistance in a 120 ohm device would be 5 ohms at maximum deflection. The traditional type of strain gauge consists of a length of metal resistance wire formed into a zigzag pattern and mounted on a flexible backing sheet, which you can see in A. The wire is nominally of circular cross-section. As strain is applied to the gauge, the shape of the cross-section of the resistance wire distorts, changing the cross-sectional area. And as the resistance of the wire per unit length is inversely proportional to the cross-sectional area, there is a consequential change in resistance. The input-output relationship of a strain gauge is expressed by the gauge factor, which is defined as the change in resistance for a given value of strain. That is, the gauge factor is the change in resistance divided by the change in strain. In recent years, wire-type gauges have largely been replaced either by metal foil types or by semiconductor types. You can see foil-based type in figure B. Metal foil types are very similar to metal wire types, except the active element consists of a piece of metal foil cut into a zigzag pattern. Cutting a foil into the required shape is much easier than forming a piece of resistance wire in the required shape, and this makes these devices cheaper to manufacture. Semiconductor types have piezoresistive elements, which are considered in greater detail later in this lecture. Compared with metal gauges, semiconductor types have a much superior gauge factor, up to 100 times better, but they are more expensive. Also, while metal gauges have an almost zero temperature coefficient, semiconductor types have a relatively high temperature coefficient. In use, strain gauges are bonded to the object whose displacement is to be measured. The process of bonding presents a certain amount of difficulty, particularly for semiconductor types. The resistance of the gauge is usually measured by a DC bridge circuit, and the displacement is inferred from the bridge output. The maximum current that can be allowed to flow in a strain gauge is in the region of 5 to 50 milliamps, depending on the type. Thus, the maximum voltage that can be applied is limited, and consequently, as the resistance change in a strain gauge is typically small, the bridge output voltage is also small, and the amplification has to be carried out. This adds to the cost of using strain gauges. Magnetic sensors utilize the magnetic phenomena of inductance, reluctance, and eddy currents to indicate the value of the measured quantity, which is usually in some form of displacement. Inductive sensors translate motion into a change in the mutual inductance between magnetically coupled parts. One example of this is the inductive displacement transducer shown here. In this, the single winding on the central limb of the E-shaped ferromagnetic body is excited with an alternating voltage. The displacement to be measured is applied to a ferromagnetic plate in close proximity to the E piece. It's this piece here. Movement of the plate affects the flux paths of this magnet and hence cause a change in the current flowing in the winding. In variable reluctance sensors, a coil is wound around a permanent magnet rather than on an iron core as in variable inductance sensors. Such devices are typically used to measure rotational velocities. This figure shows a typical instrument in which a ferromagnetic gear wheel is placed next to the sensor. As the tip of each tooth on the gear wheel moves toward and away from the pickup unit here, the change in magnetic flux in the pickup coil causes a voltage to be induced in the coil whose magnitude is proportional to the rate of change of flux. Thus, the output is a sequence of positive and negative pulses whose frequency is proportional to the rotational velocity of the gear wheel. Eddy current sensors consist of a probe containing a coil, as shown here, that is excited by a high frequency, typically 1 megahertz. This is used to measure the displacement of the probe relative to a moving metal target. Because of the high frequency of excitation, eddy currents are induced only in the surface of the target, and the current magnitude reduces to almost zero at a short distance inside the target. This allows the sensor to work to measure the displacement of very thin targets, such as the steel diaphragm of a pressure sensor. The eddy currents alter the inductance of the probe coil, and this change can be translated into a DC voltage output that is proportional to the distance between the probe and the target. Measurement resolution as high as 0.1 millimeter can be achieved. The sensor can also work with a non-conductive target if a piece of aluminum tape is fastened to the target. A Hall effect sensor is a device that is used to measure the magnitude of a magnetic field. It consists of a conductor carrying a current, seen here, that is aligned orthogonally with the magnetic field. This produces a transverse voltage difference across the device that is directly proportional to the magnetic field strength. For an excitation current I and a magnetic field strength B, the output voltage is given by V is equal to KIB, where K is known as the Hall constant. The conductor in Hall effect sensors is usually made from a semiconductor material as opposed to a metal, because a larger voltage output is produced for a magnetic field of a given size. In one common use of the device as a proximity sensor, the magnetic field is provided by a permanent magnet that is built into the device. The magnitude of this field changes when the device becomes close to any ferrous metal object or boundary. The Hall effect is also commonly used in computer keyboard buttons, keys. When a key is pressed, a magnet attached underneath the button moves past a Hall effect sensor. This generates an induced voltage in the sensor, which is converted by a trigger circuit into a digital output. Such push button switches can operate at high frequencies without contact bounce. Piezoelectric transducers produce an output voltage when a force is applied to them. They can operate in the reverse mode as well, where an applied voltage produces an output force. They are frequently used in ultrasonic transmitters and receivers. They are also used as displacement transducers, particularly as part of the device's measuring acceleration, force, and pressure. In ultrasonic receivers, the signal amplitude is a sinusoidal wave, and variations in the ultrasound wave are translated into a sinusoidal change in the amplitude of the force applied to the piezoelectric transducer. In a similar way, the translational movement in a displacement transducer is caused by mechanical means to apply a force to the piezoelectric transducer. These transducers are typically made from piezoelectric materials. These materials have an asymmetrical lattice of molecules that distorts when a mechanical force is applied to it. This distortion causes a reorientation of electric charges within the material, resulting in a relative displacement of positive and negative charges. The charge displacement induces surface charges on the material of opposite polarity between the two sides. By implanting electrodes into the surface of the material, these surface charges can be measured as an output voltage. Ultrasonic devices are used in many fields of measurement, particularly for measuring fluid flow rates, liquid levels, and translational displacements. Ultrasound is a band of frequencies in the range above 20 kilohertz that is above the sonic range that human ears can hear. Measurement devices that use ultrasound consist of one device that transmits an ultrasound wave and another device that receives the wave. Changes in the measured variable are determined either by measuring the change in time for the ultrasonic wave to travel between the transmitter and receiver, or alternatively by measuring the change in the phase or frequency of the transmitted wave. The most common form of ultrasonic element is a piezoelectric crystal contained in a casing, as shown here. Such elements can operate interchangeably as either a transmitter or a receiver. These are available with operating frequencies that vary between 20 kilohertz and 15 megahertz. This chapter has revealed some physical properties that are used in measurement sensors. The first principle covered was capacitance change, which we found was based on two capacitor plates with either a variable or fixed distance between them. We learned that sensors with a variable distance between the plates are primarily used for displacement measurement, either as displacement sensors in their own right or to measure the displacement within certain types of pressure, sound, and acceleration sensors. The alternative type of capacitive sensor where the distance between the plates is fixed is typically used to measure moisture content, humidity values, and liquid levels. Moving on to resistance change principle, we found that this is used in a wide range of devices for temperature measurement, resistance thermometers and thermistors, as well as displacement measurement, strain gauges, and piezoresistive sensors. We also noted that some moisture meters work on the resistance variation principle. We then looked at sensors that use the magnetic phenomenon of inductance, reluctance, and eddy currents. We saw that the principle of inductance change was mainly used to measure translational and rotational displacements. Reluctance change was commonly used to measure rotational velocities, and the eddy current effect was typically used to measure the displacement between a probe and a very thin metal target, such as the steel diaphragm of a pressure sensor. Next, we looked at the Hall effect. This measures the magnitude of a magnetic field and is commonly used as a proximity sensor. It's also employed in computer keyboard keys. We then moved on to piezoelectric transducers. These generate a voltage when a force is applied to them. Alternatively, if a voltage is applied to a piezoelectric transducer, an output force is produced. A common application is in ultrasonic transmitters and receivers. They are also used to measure displacement transducers, particularly of part of devices measuring acceleration, force, and pressure. Another subject of study was strain gauges. These devices exploit the physical principle of a change in resistance when the metal wire that they are made from is stretched or strained. They can detect very small displacements and are typically used within devices like diaphragm pressure sensors to measure the small displacement of the diaphragm when a pressure is applied to it. We looked into some of the science involved in strain gauge design, particularly in respect to the alternative materials used for the active element. We also discussed ultrasonic sensors. They are commonly used to measure range, translational displacements, fluid flow rate, and liquid level. We learned that ultrasonic sensors work in one of two ways, either by measuring the change in time for an ultrasound wave to travel between a transmitter and a receiver, or by measuring the change in phase or frequency of the transmitted wave. That ends this lecture on sensor technologies. See you in cyberspace.